Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The physicist who broke reality and taught us how to question the universe. Picture this. There's a sealed box. Inside, a cat according to the rules of quantum physics. That cat is, somehow, alive and dead at the same time. Not a metaphor, not a late-night philosophy debate, hard physics. And the person who proposed this wasn't a madman trying to be clever. He was a scientist who helped rewrite how humanity understands reality itself, or in Schrödinger. But here's the twist. The cat isn't the real shock. The real shock is that Schrödinger forced us to admit something deeply uncomfortable. The universe might not run on certainty the way we thought it did. So today, we're stepping inside the mind of a scientist who was equal parts romantic thinker, intellectual rebel, and razor-sharp mathematician, to see how our idea of reality got flipped on its head. Let's rewind to late 19th century Vienna. At the time, Vienna wasn't just a city. It was an intellectual pressure cooker. Artists were redefining expression. Philosophers were questioning meaning. Scientists were poking holes in long-standing assumptions. Ideas didn't just circulate here. They collided. And in 1887, right in the middle of this cultural storm, a child was born who would later help overturn centuries of physical intuition. Erwin Schrödinger didn't grow up in what you'd simply call an educated household. A better description would be a home where curiosity was treated like oxygen. His father, Rudolf, ran a successful business manufacturing industrial materials. That paid the bills, but it wasn't what made the house buzz. Rudolf was a passionate amateur scientist, the kind of person who couldn't look at a natural phenomenon without asking, "What's really happening here?" Dinner table conversation didn't revolve around gossip or routine. It revolved around experiments, plants, mechanics, and the strange behavior of the natural world. In many homes, a curious child hears, "Don't touch that, you'll break it." In Schrödinger's home, the message was closer to, "Touch it, and tell me what you discover." Science wasn't confined to textbooks. It was scattered across workbenches, embedded in tools, hiding in everyday objects. Curiosity wasn't extracurricular. It was normal life. And if you think about it, environments like that shape more than knowledge. They shape expectations. When you grow up believing the world is meant to be investigated, not just accepted, questioning becomes second nature. His mother, Georgine, brought a different kind of richness. Her background leaned toward culture, language, and academic life. Conversations flowed easily between German and English. There was no rigid lesson time, just constant dialogue. That kind of bilingual upbringing does something subtle but powerful. It trains the brain to switch frameworks, to hold multiple interpretations at once. In other words, it teaches cognitive flexibility. And that skill would later become priceless. Quantum physics demands a mind comfortable with paradox. It asks you to accept that something can behave like a particle and a wave. That outcomes can be probabilistic, not predetermined. It's not linear thinking, it's mental gymnastics. Long before Schrödinger encountered the word quantum, his upbringing was quietly preparing him for exactly that kind of intellectual terrain. In this household, asking questions wasn't seen as disrespect. It was encouraged. His parents weren't obsessed with giving immediate answers. They cared more about whether he kept digging. That cultivates a rare mindset. Patience with uncertainty, a fascination with complexity. Many great scientists later say their journey didn't start with formal education. It started with childhood wonder. That moment of staring at the world and thinking, "Wait, how does that work?" For Schrödinger, that wonder wasn't occasional. It was daily life. He wasn't being molded into a model student who memorized facts. He was growing into someone who instinctively questioned assumptions. And history shows us something important. The biggest scientific revolutions rarely begin with grand proclamations. They begin with someone, often young, often stubborn, asking a deceptively simple question: why does it have to be this way? That habit of questioning would one day help shake the foundations of classical physics, because when curiosity is nurtured instead of silenced, the impossible starts looking negotiable. And this was only the beginning. You could say it all started in a very ordinary living room in Vienna. When young Schrödinger first walked into his academic secondary school, nothing about him screamed future revolutionary physicist. To most people, he looked like the ideal student, quiet, disciplined, consistently at the top of the class. But it didn't take long for teachers to notice something unusual. He didn't study the way the system expected. He loved mathematics, not for grades, not for praise, but for the strange elegance hiding inside it. Where other students saw formulas as tools to get through exams, he saw structure, rhythm, almost beauty. A proof wasn't something to memorize, it was something to inhabit. He could spend an absurd amount of time staring at a single derivation, not trying to copy it, but asking, why does this work? What makes this structure hold together? If a theorem was presented as something to simply accept, it bothered him. For Schrödinger, knowledge wasn't a list of answers, it was a trail you had to walk yourself. As the saying goes, give a man a formula and he'll pass a test, teach him to question it, and he'll change a field. That mindset didn't always mesh smoothly with early 20th century schooling, which leaned heavily on discipline, repetition, and standardized recall. Mechanical memorization felt like wearing shoes 2 sizes too small, technically functional, deeply uncomfortable. When teachers demonstrated a method and expected silent imitation, Schrödinger often pushed back with a simple, dangerous question: why does it have to be done this way? Not rebellion for its own sake, curiosity refusing to sit quietly. He wasn't satisfied with landing on the right answer. He wanted to understand why the question existed in the first place. This gave his thinking a fascinating dual character. On one side, rigorous logic sharpened by mathematics. On the other, a philosophical imagination fed by literature, language, and culture. Science, to him, wasn't cold calculation. It was humanity's most ambitious storytelling project about how the universe works. Outside the classroom, he read widely philosophy, natural science, essays that tried to stitch different domains together. While classmates focused on assignments, he drifted toward bigger questions. Is reality really what it appears to be? Are laws discovered or invented? Does nature speak a hidden language? None of that was on the exam, but it was shaping the architecture of his mind. Teachers later remembered that his defining trait wasn't raw memory, it was persistence in understanding. He would rather wrestle with a concept all day than accept a neat explanation that didn't feel earned. In a test-driven system, that kind of slow, deep thinking isn't always rewarded. In science, it's gold. During these formative years, he absorbed a quiet conviction: science isn't just about predicting outcomes, it's about seeing the machinery underneath. That belief would later steer him straight into the heart of quantum theory, where certainty begins to wobble and complexity isn't a bug, it's the feature. Long before he ever touched quantum physics, he was learning something more fundamental: how to think, not what to think. And that's often the earliest sign of someone destined to shake a discipline. Then history intervened. In 1914, Europe tightened like a drawn bowstring. Lecture halls still echoed with equations. But outside, events were accelerating. Schrödinger, just stepping into his academic life, found himself swept into World War I. For a theoretical mind, war isn't an abstraction. It's mud, cold air, strict orders, and the constant uncertainty of what the next minute might bring. Assigned to artillery-related work, he dealt with trajectories, measurements, and the brutally practical side of mathematics. It was a harsh irony. The same equations used to describe nature were now tools of destruction. Logic had consequences measured not in grades, But in lives, when calculations leave the blackboard and enter the battlefield, theory feels very different. War didn't just expose him to technology, it confronted him with unpredictability. In textbooks, equations promise precision. On the front lines, weather, human error, and chaos rewrite outcomes without apology. As another saying goes, no plan survives first contact with reality. That gap left a mark. The tidy, deterministic universe promised by classical physics suddenly looked more like an idealization than a guarantee. Real systems were messy, sensitive, full of variables you couldn't tame. In quiet moments between duties, he kept reading and reflecting, not to escape the situation, but to wrestle with a deeper question: if reality is this unstable, how should science describe it? This wasn't career anxiety, it was philosophical pressure. Should science only model perfect order, or must it also account for uncertainty? War forced him to confront whether humanity's rational frameworks were robust enough to handle lived experience. Slowly, that tension nudged his intellectual compass. He grew increasingly skeptical of strict determinism and more intrigued by ideas of probability, fluctuation, and wave-like behavior. Seeds were being planted, seeds that would later bloom in the strange landscape of quantum physics. Sometimes the road to scientific revolution doesn't run through laboratories. Sometimes it runs through history itself. When quantum theory finally burst onto the scene, Schrödinger didn't just learn it fast because he was good at math. He understood it because life had already taught him something deeper. Certainty is fragile. War has a way of stripping illusions. By the time Europe staggered out of destruction, the old promise that the universe behaved like a perfect clock felt naive. And Schrödinger changed with that world. He stopped chasing the satisfaction of getting the right answer. Instead, he began asking a more unsettling question: how does science deal with uncertainty itself? That shift wasn't academic, it was philosophical. Because quantum theory doesn't politely extend classical intuition, it breaks it. At its core lies an uncomfortable admission: nature does not always behave the way common sense says it should. In a strange way, the battlefield had prepared him, not technically, but mentally. It taught him intellectual humility. Before you can understand reality, you must accept that reality refuses to be predictable. That realization transformed physics from an abstract puzzle into something more honest, a language for negotiating complexity. So when Schrödinger later wrote equations describing probabilistic waves, he wasn't just inventing mathematics, he was continuing a conversation with uncertainty that life had already started. From that tension between order and unpredictability emerged a more mature thinker. Theory had finally collided with reality. Public memory often reduces Schrödinger to a chalkboard genius, the man who wrote an equation that reshaped physics. But step away from the equations, and you find a life that didn't exactly follow classical mechanics either. In the 1920s, he married Anne-Marie. On paper, it looked like the model academic marriage: respectable, orderly, perfectly aligned with expectations. Reality, however, had other plans. Schrödinger's worldview, including his views on love, leaned heavily toward personal freedom. He and his wife navigated a relationship structure that was unusually open for their time. Not scandal-driven chaos, more like a quiet rebellion against rigid templates. He believed emotional life was too rich to fit into neat categories. Much like nature itself, you might say his romantic philosophy mirrored his physics. Certainty was optional. Friends and colleagues described him as disarmingly candid. He could spend the afternoon dissecting wave functions and the evening discussing poetry, relationships, or existential worries. There was no firewall between intellect and humanity. His personal life was undeniably complex, but not careless. If anything, it reflected a stubborn commitment to honesty and autonomy. To Schrödinger, understanding the world meant understanding human experience too. Science and life weren't separate compartments. They were chapters of the same story. This attitude wasn't exactly mainstream in an era obsessed with social order. But those who knew him well often noted he wasn't trying to rebel. He simply refused to live inside boxes that didn't fit. The same instinct later shaped his response to quantum theory. When reality contradicts your framework, don't ignore reality. Rewrite the framework. His lifestyle echoed his scientific spirit. Embrace complexity. Allow multiple possibilities. Resist oversimplification. That didn't mean rejecting responsibility. Quite the opposite. He valued clarity and communication. In a culture built on appearances, radical honesty felt almost avant-garde. Looking back, his personal life isn't gossip attached to genius. It's part of the architecture of his thinking. A scientist willing to challenge physical laws is often equally willing to question social ones. In Schrödinger, rationality and emotion weren't rivals. They were partners in a shared belief. The world, including human relationships, is more intricate than any single rulebook. Maturity isn't about flattening complexity. It's about learning to live with it. That mindset made him not just a quantum pioneer, but one of the era's rare intellectual free spirits. After the war, Europe tried to rebuild its cities, but its intellectual foundations were quietly shifting. Classical physics, once thought unshakable, began showing cracks. And right in the middle of this tremor, Schrödinger entered a restless phase of his academic life. He became a traveler of ideas, teaching here, debating there, absorbing new methods everywhere. Each university stop felt less like a job and more like stepping into a laboratory of thought. In Jena, new mathematical tools expanded his vocabulary. In Stuttgart, theory debates sharpened his instincts. In Breslau, young scholars challenged assumptions with contagious urgency. These weren't just locations on a map, they were intellectual crossroads. Across Europe, physics was undergoing a quiet revolution. Atomic theory was wobbling. Classical mechanics struggled to explain microscopic behavior. Mathematical innovation outpaced philosophical comfort. The atmosphere felt electric. Everyone sensed the old worldview was dissolving, but no one could yet see the replacement. Schrödinger stood exactly where those currents met. Academic discussions swirled around electrons, spectra, energy structures, conversations that often ended without answers but always produced better questions. For him, this wandering period wasn't instability, it was acceleration, like calibrating instruments inside a storm. He was searching for a new language to describe nature. Then a provocative idea gained momentum. Maybe particles weren't tiny billiard balls at all. Maybe they behaved like waves. It was beautiful and dangerous. Accepting it meant abandoning centuries of mechanical intuition. Many researchers hesitated. Schrödinger leaned in, not because novelty is seductive, but because the idea opened a door. Perhaps reality operates in abstractions deeper than our everyday metaphors. And when the mathematical structure finally began to click into place, he sensed it immediately. He was touching a boundary. Moments like that don't feel loud, they feel inevitable. A turning point was approaching, the kind history only recognizes in hindsight. And then, a theory arrived that changed everything. By the late 1920s, quantum mechanics had reached an awkward milestone. It worked. Not kind of worked. Not the math is promising. It predicted experiments with eerie precision, the kind that makes scientists double-check their instruments. There was just one tiny problem. Nobody could agree on what the theory was actually saying about reality. Physicists found themselves in a surreal position. The equations were flawless, while intuition had completely clocked out. And right in the middle of that confusion, Erwin Schrödinger decided to do something theatrical. By scientific standards. Anyway, he wasn't content arguing inside equations. He wanted to drag quantum weirdness into everyday experience. No microscopes, no obscure lab setups, just a scenario anyone could picture. So, he reached for a cat, a box, 4 objects, and a philosophical detonation. Picture a sealed box containing A radioactive atom that might decay, a detector wired to that decay, a poison mechanism triggered by the detector on a completely unsuspecting cat. Quantum theory says that before observation, the atom exists in a superposition, decayed and not decayed. If the device is tied to that state, logic snowballs fast. The cat must also be in superposition, alive and dead at the same time. Pause there. Because this isn't dark humor. This is what happens when you follow quantum math to its literal conclusion. And Schrödinger's point wasn't cruelty or shock value. He was exposing attention. If the theory applies to atoms, it must apply to everything. Cats, observers, reality itself. Most listeners hit the brakes right here. Okay, that can't be real. Exactly. That discomfort is the experiment working. The cat was never the real subject. Schrödinger wasn't asking about animals. He was asking, when does reality commit to a single outcome? During the physical process, or when someone opens the box? If observation determines what becomes real, then the universe stops looking like a pre-written script and starts resembling an interactive performance. This idea struck at the heart of the interpretation championed by Niels Bohr and Werner Heisenberg. The view that physics describes measurement results, not hidden objective states waiting backstage. In plain English, nature doesn't owe you an answer until you ask the question. For minds trained in classical physics, this felt like intellectual whiplash. Newton's universe was a clockwork machine. Quantum reality looked more like a probability novel. And as the saying goes, truth is stranger than fiction. Especially when fiction still follows intuition. A collective shock to the scientific psyche. The real power of the cat experiment wasn't biological, it was psychological. It forced a stark choice. Do you trust the math, or your instincts? Reactions across the community felt almost scripted. Mathematicians, the equations are solid. Experimentalists, the data agrees. Philosophers, hold on. This changes everything. Everyone else, what did the cat do to deserve this? Ironically, Schrödinger meant the thought experiment as a critique, a spotlight on how absurd quantum interpretation could seem. Instead, the cat became the most successful ambassador quantum physics ever had. Suddenly, abstract debates became dinner table questions. Does observation shape reality? Is probability ignorance? Or nature itself? Do possibilities coexist before measurement? Nearly a century later, those questions still fuel research and philosophy alike. The cat never retired. Because it isn't really about physics. It's about the limits of how humans picture reality. And that makes it timeless. After the uproar faded, something fascinating happened. Quantum mechanics stopped being that weird theory and became impossible to ignore. Because it kept working. Experiment after experiment confirmed it. Calculations delivered. Predictions landed. Even skeptics had to admit, whether intuition liked it or not, the theory described the world. And at the center of that shift stood Schrödinger. His wave mechanics didn't just patch holes, it gave quantum theory structure. Electrons stopped behaving like mysterious jumps and started appearing as calculable wave patterns. It was like installing steering and navigation in a vehicle that already moved but made no sense. Suddenly, the microscopic world felt navigable. From radical idea to global recognition, by the early 1930s, it was clear this wasn't a passing phase. Physics had adopted a new language. In 1933, that shift received formal acknowledgement when Schrödinger shared the Nobel Prize in Physics with Paul Dirac. The symbolism mattered as much as the science. It was the international community saying, the quantum revolution is official. Classical physics explained planets and engines. Quantum physics unlocked atoms and matter itself. The scientific map had been redrawn. Quantum mechanics was never a solo act. It was a constellation moment. But Schrödinger's contribution was uniquely transformative. He didn't just add results. He changed how the theory was expressed. His equation allowed scientists to calculate atomic structures, predict electron behavior, and understand chemical bonds with unprecedented precision. That moved quantum theory out of philosophical debate and into engineering reality. The technologies that would later reshape civilization, semiconductors, lasers, advanced materials, all grew from this mathematical foundation. If classical physics built the bridges of the visible world, Schrödinger's framework gave humanity the tools to start construction in the invisible one. And once that door opened, there was no going back. At some point, Schrödinger's authority in physics stopped being about equations. Lots of scientists can write powerful formulas. What made Erwin Schrödinger stand out was something rarer. He never stopped asking what those formulas meant. While much of the physics community focused on getting the right numbers, he kept circling a deeper question. What reality is this theory actually describing? That put him in an unusual position, both architect and critic of the quantum revolution. And paradoxically, that tension is exactly what drives science forward. Because progress isn't just built on answers. It depends on someone asking, do we really understand what we just calculated? Here's the twist that makes the story satisfying. The same physicist who used a thought experiment about a cat to question quantum theory eventually became one of its central authorities. Not because he stopped doubting, but because science itself runs on a loop. Question, breakthrough, verification, new doubt. That cycle isn't a flaw. It's the engine, and modern physics was forged inside it. When abstract math becomes machinery, as quantum theory matured, something remarkable happened. It stopped being philosophically strange, and started being technologically unstoppable. Take lasers. They're not magic beams. They're precision tools built from quantum transitions. Scientists learned how atoms absorb and emit energy, how light interacts with matter, and how wave behavior can be engineered instead of merely observed. The results reshaped entire industries. Laser surgery that cuts without contact, fiber optic communication that moves information at light speed, measurement systems with astonishing accuracy. Materials science followed the same path. Instead of blind trial and error, researchers began predicting material behavior using quantum models. Superconductors, nanostructures, functional materials, all of them are, at their core, engineered wave behavior. It's a reminder of an old saying: today's theory is tomorrow's toolkit. Computing with the rules of nature. One of the boldest frontiers today is quantum computing, not simulating quantum effects, but using them directly. In this paradigm, quantum states aren't side effects, they're the hardware. And understanding how those states evolve still traces back to the same wave framework Schrödinger introduced. Modern platforms built by companies like IBM and Google are essentially attempts to turn theoretical physics into information infrastructure. That's a profound shift. We may be entering an era where computation itself follows quantum logic, not classical shortcuts layered on top. And that's not science fiction. That's engineering catching up to theory. The invisible layer of everyday life. Here's the part that feels almost poetic. The math that once looked detached from reality now sits underneath daily life. Every time you unlock a phone, transmit a signal, or store data, quantum rules are quietly doing their job. The path looks like this: abstract theory, mathematical structure, engineering systems, everyday experience. Science plants its seeds in abstraction, and decades later, you're holding the forest in your hand. So when someone says, every swipe on your screen uses Schrödinger's math, that's not metaphor. It's a compressed version of technological history. A physicist walks into biology. At this point, most stories would stay inside the physics lab. But Schrödinger took a sharp turn toward an older, bigger mystery. What is life? Not philosophically, physically. In the 1940s, biology could describe inheritance but didn't yet understand its structural basis. Schrödinger stepped in with a physicist's toolkit and a willingness to cross boundaries. The result was a slim but explosive book, What is Life? It wasn't an experiment log, it was an intellectual spark. He argued that life doesn't violate physics, it exploits it. Key ideas followed: Genetic information must live in stable structure. Sorter can arise from statistical laws, biological systems, or physical information carriers. His core insight was radical for the time. Life is, in part, an organized flow of information. Today that sounds obvious. Back then, it helped push biology toward molecular mechanisms, a shift that would eventually fuel genetics and modern biophysics. Sometimes a good question is more catalytic than a finished answer. When physics collides with philosophy. By now, the story has drifted beyond physics history. And that's not an accident. Quantum theory didn't just change how we predict atoms. It forced humanity to revisit an ancient question. What is reality? Schrödinger resisted treating quantum mechanics as a mere calculation engine. For him, a successful theory demanded interpretation. If the math describes the world, what is it saying about existence? That question pulls physics straight into philosophical territory. Quantum theory introduces an unsettling character, the observer. In classical physics, observation is passive. In quantum mechanics, measurement appears intertwined with outcome, which raises uncomfortable possibilities. Are we revealing reality, or participating in it? Schrödinger explored whether consciousness is external to nature, or embedded within its structure. Not mysticism, but a rigorous attempt to reconcile theory with experience. Meanwhile, another tension emerged. The microscopic world behaves probabilistically. The everyday world feels solid and predictable. How do those realities coexist? Schrödinger warned against confusing mathematical success with genuine understanding. Equations can guide us, but they don't automatically tell us what the world is. And that leads to a bigger reflection. Science may not be a machine that prints final answers. It's a method for expanding the horizon of understanding. When theories feel counterintuitive, that doesn't necessarily mean nature is broken. It might mean our intuition needs an upgrade. Quantum mechanics is therefore more than a scientific milestone. It's a philosophical shockwave. It reminds us that reality isn't obligated to match human expectations, and that discovery often begins where comfort ends. Which leaves us with a lingering question. If reality itself runs on probability, what exactly are we living inside? There's still no universal answer, but the act of asking keeps pushing the boundary outward. And that journey is far from over. By this point, what we've been looking at isn't just the biography of a physicist anymore. It's a chain reaction of ideas. Science leads to technology, technology reshapes culture, culture forces us to rethink reality itself. And somewhere near the center of that chain, you keep running into the same name, Erwin Schrödinger. His legacy isn't just an equation tucked inside textbooks. It's a shift in how humanity talks to the universe. Not louder, smarter, more humbly. From equation to civilization. What began as math describing tiny particles didn't stay small for long. First, it powered the hardware of the information age. Semiconductors, communication systems, modern electronics. Then it became a precision tool for lasers, materials engineering, and technologies that once sounded like science fiction. It even crossed into biology, helping scientists think about life not just as chemistry, but as organized information. And the ripple didn't stop in laboratories. Quantum ideas slipped into philosophy, science fiction, and everyday language. We started talking differently about uncertainty, possibility, and what it even means for something to be real. Very few scientific frameworks travel that far, and the reason isn't technical complexity, it's perspective. The universe stopped looking like a clockwork machine and started resembling something richer, a layered system of probabilities, structure, and information. At that point, science isn't just explaining the world, it's rewriting the vocabulary we use to describe it. As the saying goes, change the lens, and the whole landscape shifts. The question that refuses to go away. The most powerful inheritance of the quantum revolution isn't a device or a breakthrough gadget. It's a question that keeps echoing. What is the world, really? Is it a fixed structure that exists independent of us, a web of probabilities? or something inseparable from observation itself? Physics hasn't settled that debate, and that's the beauty of it. The greatest intellectual legacies don't shut doors, they open better ones. They sharpen the questions until ignoring them is no longer an option. The journey that doesn't end. Looking back, you can trace a remarkable arc, an abstract formula, technological civilization, a new framework for understanding reality. And the story doesn't land on a final answer, because science was never meant to deliver certainty wrapped with a bow. Its real power lies in expanding the horizon, pushing the edge of what humans can meaningfully ask. Schrödinger didn't hand us a neat conclusion. He made the mystery deeper, clearer, and far more interesting. And that's often how transformative ideas work. They don't close the book, they make you want to keep reading. Because in science, as in life, the frontier is where the story really begins. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.